Okay, I guess we can start. So in the first part, maybe we want to kind of repeat what we learned yesterday, or at least the important part. So part of the lecture was kind of trying to convince you that these kind of operators exist. So we found that actually at domain walls between a p-wave superconductor and an insulator, there's a state at zero energy, and it's described by an operator, which is a Hermitian. But still fermionic in the sense that kind of two of such operators anti-commute with each other. So the question was what is the connection to a, let's say, a usual fermion? And the connection to a usual fermion was that you have to pair up two of them. And then these two real fermions form one complex fermions. Yeah. This is very similar to, I don't know, if you have electromagnetic field and you have creation and annihilation operator, you have like momentum and position, so P and Q, or electric field, or yesterday with this surface acoustic wave, it would be the position in the z direction. So that's a physical observable. But in order to have like an oscillator, you need to have two and make a creation operator out of them, yeah, with the real and imaginary part. But now for fermions, these are actually not observables, these two. Yeah, observables are kind of always bosonic operators. So it's a bit more weird in this sense. But otherwise, it's the same, yeah? So, I mean, we can never hope to measure a complex quantity, so we kind of take the real and imaginary part of it. Okay. So then I kind of explained to you how you get the qubit out of this. And I said, yeah, you need 4 Majorana fermions. And by 4 Majorana fermions, we always think that we have like a p-wave superconductor in the background, and then an insulator, and again a p-wave superconductor, and then again an insulator. So a single such, this is called domain wall, is described by the Chekhov and Rebbe model and gives you a zero energy state. But this bound state decays exponentially. So if I keep these two far apart from each other, I can say I kind of have one solution here and one solution here, and they kind of don't talk to each other up to exponential accuracy. Same thing here. So this brown one is a p-wave superconductor. Or the brown one was the mu bigger than 0, and the white one was the mu smaller than 0. So how do I get now a qubit out of this? Does anybody remember? I mean, first, in what kind of space these 4 Majorana operators act? What was the Hilbert space of these operators? Or Fock space, how we called it. So we had this trick. Yeah?
Well, we had to exchange the Majoranas.
We had to exchange the Majorana. No, to operate we had to exchange. But first I'm just asking you how to encode a qubit in this. Somebody knows? So the trick was to actually pair up 2 Majorana fermions and make one conventional fermion out of it. And for a conventional fermion, we have Fock space, which says we can have the fermionic mode either empty or occupied. Okay? So this is what we called, so the gauge is what we call this, the way how we pair them up. And each of these ways, the fermionic mode can be either empty or occupied, yeah? So this is either or. Maybe I should denote it differently. Either empty or occupied. And the same thing here. And in the end, the wave function is kind of a product of these two. Yeah? So we have 4 possibilities. Now we have the possibility that the left mode the left, conventional fermionic mode is either empty or occupied, and the same with the left. So there's 4 possibilities. So this doesn't look like a qubit to me. Yeah? It's a 4-level system. So how one gets from this 4-level system to a qubit? Or why one should think about this 4-level system as a qubit, as a single qubit? Yeah? Yeah, because the fermion parity actually cannot be changed. First we will see, or we will not see, but it's kind of clear that under braiding we cannot change the fermion parity. So whatever braids you do, because a Hamiltonian, a physical Hamiltonian can only create fermions in pairs. So a braiding operation is kind of executing some physical Hamiltonian. So it will never bring you from this state to that state. If you start out in this state, you might end up in this state, but never in this state. There's like a line in between. So the operation of the braiding never brings you from something like this to something like this. And then we said, yeah, but we say, the system is isolated enough that we never actually tunnel a single electron from somewhere outside inside. So there's actually never a process which leaks you in here. So this would be states which would be leakage states. So you have to kind of suppress processes which go here. So you should remove them completely from your description. And you end up with a qubit. Okay. So what is special about this qubit, and this I maybe didn't explain in enough detail, is that such a system as I drawn here has the following spectrum. There are excitations above what I called M bar. Then there's 0. And then there are excitations below M bar. So M bar is kind of the gap of the superconductor. So these were the states of the Jackiff and Rebbe model, which were like the extended states. And then we had these 4 states in here, which basically were sitting, the 4 Majorana fermion states, which were basically sitting at 0 energy. And in order to describe what they actually mean, we combined them in 2, and this is the Hilbert space. Yeah? So this Hilbert space, which I'm talking about, actually lives at 0 energy. So it's not a conventional qubit which you might have. Usually you have like a magnetic field applied to your qubit, and there's like rotation going on. This is really a qubit where the 2 energy levels are at the same energy. And as long as you keep these Majorana particles far away from each other, they remain at the same energy. Okay? So that's useful in one way and not useful in another way. If you want to operate on it, it's very much not useful. If you don't want to operate it, then I can guarantee you that maybe they shift up and down together, but they never have like a shift between them. There will be never dephasing of this memory. Okay? So it's a completely different kind of qubit than what you're used to. For example, what Hendrik Bloom explained to you about the spin qubits, where there's always an external field applied to it, and you go in a rotating frame and whatever, so it's complicated. So here is never a magnetic field applied. Okay? Out of these 4 Majorana fermions, there are 2 states which form your qubit, which are exactly at 0 energy, and then the rest of the states are far away. Okay? So that's a qubit and the encoding of the qubit. So then already yesterday there was the question, so how would I operate on this qubit? I give you a qubit and I can guarantee you that the 2 states never go up and down with respect to each other. So you tell to me, yeah, it's great for quantum memory. I encode something there and it will forever stay there. But how you measure it and how you operate on this, it's absolutely unclear. So there this dream comes into the game, or the idea of topological quantum computation, which was the following. And maybe now you can understand actually this part a bit more in detail. Or if you still don't understand everything, it's okay, because we'll explain this idea in more detail in this lecture. Okay? So we start out in vacuum. That was the idea. And then we generate two particles in a pair. And we generate another two particles in a pair like this. And we do something like this. Okay. So again, these are the world lines of the particles, what I've drawn here. Okay? And so what I do is particle 1 is space and time stays at the position. So let's call it gamma 1. It stays exactly where it was with a little bit of wiggling. And gamma 4 also stays exactly where it was. And gamma 2 and gamma 3 swap places. Okay? So it's very hard to imagine on a nanowire like this. But now for a moment, just imagine that these were kind of embedded in some kind of 2D materials that you could really move them around each other. Yeah? In order that I can do this, I need to have a two-dimensional space here. So I start in a vacuum, which means for me in the state 0, 0. Yeah? Qubit. That's the initialization step. And then I generate them out of the vacuum. And generating them out of the vacuum is just, I started with a completely insulating state. And then I introduce a little bit of P-wave superconductor here. And that's exactly the step which does this, yeah? And the same thing here. So the braiding I cannot show you here because, okay, but we'll see later how the braiding is done. So then you move these two around each other. And then you do something up here which is called fusion. So this middle part is braiding. And the fusion is just, you shrink this P-wave, this topological region again to 0. And you ask yourself whether at the end there's 0, 0 coming out, which most of you would say it's automatic that 0, 0 comes out. But I tell you, there's also the possibility that actually 1, 1 comes out with certain probabilities. And this is your computation, yeah? It looks very much like a normal quantum computer now. And then you reset again in the vacuum and do some other braid. This is called a braid, yeah? And so the two steps which are special here, one is there's no dephasing, exactly. This is what we explained before. The second is operation which you do on this qubit. Actually, it just depends on the braid which you do. And braid means, you know, they make a knot, these two, you see? But it doesn't matter whether you little bit wiggle around. Don't do it perfectly. Okay? So that's the idea. So the type of knot which you do in space-time, that determines the gauge which you execute, not exactly how you do. Okay? So that's the main idea. So now, step by step, I try to explain to you how the fusion, because this vacuum initialization, I think you understand now. I explained to you how the fusion works, and then I explained to you maybe a bit, not in all the details, how the braiding works. And then we'll see how long this takes. So actually, I forgot a bit my numbering, but I don't know, 2 times 3, I don't know. Fusion. And the fusion is rather easy. Or at least how I will explain it to you now. So the fusion is the process where you actually shrink this P-wave region to 0. Yeah? So we introduce a parameter which is called d, which is the distance between these two Majorana fermions. D. And we ask ourselves what happens to the spectrum. And we know kind of if d is large compared to a scale, which is like given by m bar. So if d is large, then it's basically two states at zero energy. Okay, this is actually blown up quite a lot. It's exponentially close to zero. So the question is what happens if I decrease d? And the fact is the following. We know from Chekhov and Rebbe model that you have these two states at zero energy, but the wave function was actually exponentially decaying. So the fact that they are exactly at zero energy was corresponding to the fact that we said they are independent of each other. But now you will actually split them to finite energy given by kind of the overlap, more or less. Okay. So the fusion is actually bringing these two together, and it's described by a Hamiltonian, which is, let me understand, delta, which is a function of the distance, times I gamma 1, gamma 2. Let me try to understand if this is correct. Because I wanted the zero state, and that had parity 1 is actually the ground state. So I will put a minus sign here and kind of claim that the delta is positive. But a lot of these signs don't matter. So it's actually minus delta as a function of d times what we call this parity operator. And the parity was nothing else than sigma c, the logical basis. Yeah? So I have like three ways to write it. I called it, I think, last time C-wiggle. Yeah? And this delta as a function of d behaves exponentially with d. Yeah. And the larger the gap is, the faster it decays. And then there's some units. Okay. So the fact is that fusion is nothing else than bringing them close together, which makes the energy of the one state go up and the energy of the zero state go down. And the scale on which this actually happens is like 1 over gap, approximately. Which is also called coherence length. It's another name which you might have heard. So you enjoy the topological protection, and you see, you call it topological because the error which you make are actually exponentially small. That's usually not the case in other types of stuff which you do. So you call it topological protection. For example, if you have 2 times this length scale, you're actually very close to 0. If this is not yet good enough for you, you go 3 times this length scale or 4 times, and it gets better and better. Yeah. So you give me an accuracy, and I tell you a number which is not so large, by which you have to keep the 2 Majoranas away from each other, and then you achieve this accuracy. And the fusion is the opposite process. You bring the 2 together, and the 2 qubit states, which were this 0, 0, they split up in energy. And once they split up in energy, I guess you know better methods than me in order to detect them. I mean, you see, I'm not going here. We will have to discuss details of your specific implementation if you want to know how to do this in whatever system you do the Majorana fermions. But typically, if you bring them close together, and always if you bring them close together, they split up in energy, and then you will typically find a good way to kind of detect this energy. Okay? So at the last step, you bring the Majoranas together, and you ask yourself whether you end up in the global ground state of the system or whether you end up in the excited state. And that's the measurement at the end. Okay. Are there questions to this part? So now you should kind of understand how the initialization and the final measurement step works. You see, it's actually very similar to the usual quantum computation case. So now you might ask, how does the operation work in between? And that will be the last step, which we try to understand. And it turns out that for these particles which are described here, this kind of operation doesn't form a universal quantum computer. Okay. They were kind of too simple. And the lecture would have gotten too complicated if I would have shown you particles which are universal. So we live with that. So we'll get some kind of operations in a topological fashion here. And then I explain what the ideas are to make this even universal. Or you might come up with a system which has more exotic particles, where actually the braiding is enough in order to do all possible operations. Yeah?
So I understand this fusion process means that you bring together two of the Majoranas separately, not all four together.
Not all four together.
Okay, so it looks very strange that if I bring just two Majorana, each of the Majoranas close together, actually both of them can go from the 0, 0 state to 1, 1 state. Because how does the first pair of Majorana equal the second pair of Majorana? They are still far apart.
Yeah, good question. And what your question implies, and that's true, that there's a huge amount of entanglement in this system. Okay. So this topological quantum computer, these are not classical particles as you might imagine them. Yeah. Already, the basis is like these two Majoranas, I put them as far away from each other as I want, and they still encode the qubit. So do the other two. So there's also a correlation between these two. Yeah. So if you ask yourself, where does the correlation come from? They come here from initially, yeah? And then it's like entanglement, which you kind of spread out through your system. And that's where kind of the computation power of this comes from. Otherwise, if they were classical particles, you can try at home with tennis balls, move them around each other and try to see if they do some kind of computation. Yeah.
How do you turn on and off the keyboard?
Yeah, so now we're talking experiments, yeah? So now it depends on the concrete implementation, and for the guitar-fire, I can tell you, I mean, you see the P wave was where the chemical potential was positive, and the insulator, I mean, it was not a real true insulator. You just expel the particles from the wire, and you do it by a gate, So you apply a gate, and you push out the electrons, and it becomes insulating. Okay. At the beginning, maybe it sounded like you cannot do it. Now it sounds much easier than it actually is. So you have to ask. There's some people in here which actually do it in experiments. So it's not as easy as it sounds from me. But there's no kind of fundamental reason why you shouldn't be able to do it. No, yeah, you don't do it by cooling down. You keep it cold all the time. Yeah. So another thing, you see, you need superconductivity. So and also, typically the temperature should be much lower than this gap here. So this will be not a room temperature quantum computer typically, unless you come up with a very, very special system which we don't know yet. Okay. So now the important step, and this is the most confusing one. It was also for me, so which is the step of braiding. Why does this do at all something? Yeah. And I try to convince you that it's not so absurd to think that it actually does something. Let's see if I manage. So we have braiding. And actually for braiding, I have to go back to your quantum mechanics lecture, which is usually called Quantum Mechanics 2, where you learned about many particle systems. And you learned that going from single particle Schrödinger equation to many particle Schrödinger equation, there was a new concept coming into the game, which was exchange statistics. And then most likely you had one of the old books which discussed the exchange statistics via the permutation group. And then you convinced yourself there's nothing else than fermions or bosons in the world. This is also what people thought for some time, but it's actually only true in 3 dimensions, but in 2 dimensions something more special can happen. And it turns out that actually the real group which one should look at if one should discuss exchange statistics is the group which describes these processes. Yeah? So exchanging two particles is not like doing this. You will never be able to do that in the lab. Yeah? You don't just do and then light off and then this. Yeah? But you move them around each other in time. So the assumption that it's all just, you replace, usually you replace x1 with x2 in the wave function, and that was it. And then you say, yeah, you get a minus sign or a plus sign. No, you do that in time. So you have to look at the whole word line, how you actually do it. So the relevant group which describes your exchange statistics is this group. And this group is the braid group. That's just a name for it. Yeah. And it's called braid group because it's kind of the same way as you maybe make your hair if your hair is a bit longer than mine. Yeah. Kind of start off. Each of these is called a strand. And you start off and then you kind of move them around each other. And that's how you braid. So let's try to formalize the braid group. And we'll see how the permutation group comes out of it. So the braid group, you have a braid group on n strands, yeah? So actually the braid group is much older than topological quantum computation. So n would be the number of Majorana fermions for us. Yeah. And the braid, the action of doing the braid is the time, obviously. So this group is kind of generated by elementary operations. And the elementary operations which you might do is kind of the following. You take particle k, and you take particle k plus 1, and you move them counterclockwise around each other. And clockwise and counterclockwise always matters a bit whether you look from top or from bottom. I think conventionally, I'm not completely sure, is to look from top. And you draw it by leaving here a little gap. Then you see which particle comes from front and which goes in back. And this you call the operation bk. Yeah? You just index it via the k. So bk meaning you braid, meaning exchange. But now in a physical process, counterclockwise, the particle k and the particle k plus 1. So the braid group is actually generated B1 up to Bn minus 1. Because the Bn minus 1 exchanges the n minus 1 particle with the n particle, it kind of doesn't make sense to have additionally the Bn, okay? Because there's no n plus 1 particle. Understand? So the bk exchanges k plus 1 in a counterclockwise fashion. And if I call the group is generated by this, then of course you also have to add the inverse of it, which is moving it the other way around, and all kinds of products which you might build. And that's what is then called the free group, okay? And that's not the braid group, because there's certain constraints on this operation. So certain kind of products of these which you might make are the same as some other types of things which you might make. So you kind of have to encode these physical pictures that you want to describe this in some kind of algebra here. And luckily, this has been done for us before. And I will be not able to convince you, I guess, that the two constraints which I write down are actually enough to kind of capture everything which you geometrically think about this. Yeah? I just write down the constraints. They will make sense, but it's not clear that these are kind of all the constraints which you have to put on top. So one constraint is actually very simple. One constraint is the following. If I first, you see, it's a group, so they don't commute, yeah? So this means I first exchange particle j with j plus 1, And then I exchange particle k with k plus 1. So the question is, when is actually the same as doing it the other way around? Do you have any feeling when this could be the same? Yeah. K being, no, then it's actually not the same. So you see. So if you change these two, you involve this particle. And then the next two, if you take this as the second braid, then it actually matters which way. Yeah? This is exactly the point where it doesn't work. So it actually works for sure, and you might convince yourself very easily that if the distance is larger or equal to, that then it actually works. Because exchanging these two and exchanging these two doesn't really matter. That means you can kind of move the braids down and up if they're far away from each other. Yeah? Because doing first is doing this first and then doing this here, but you might do this first and this. Yeah? So that's kind of the same braid. You wouldn't call it a different braid. Okay. But that's still the easy constraint. The more complicated constraint is the Young-Baxter. And I convince you that this is true. And then you have to believe me that these two constraints on the free group are enough to kind of encode your physical picture about braiding. So Young-Baxter is actually also very easy to write down. If f bk, so this is actually true for all k and j obeying this. And the Young-Baxter tells you if you first exchange k and k plus 1, then k plus 1 and k plus 2, and then again k and k plus 1, it's actually the same as doing this. So first k and k plus 2, then k and k plus 1, then k and k plus 2. Okay. It's not immediately obvious that this should be the case. So let me try to draw a picture, and then we see if it becomes obvious. So I mean, for the other one, I didn't draw a picture. It's really just moving them up and down. So let me draw the picture for the Young-Baxter. So let me draw the left-hand side. So we have k, k plus 1, and k plus 2. These are the only particles involved. Yeah? So this relation should be true for all k, of course. Yeah? But we take just 3 of them. So the left-hand side tells you you should replace k and k plus 1 in a counterclockwise fashion first. OK, done. And the k plus 2, of course, goes up here. And now I will not have enough space, so I have to redraw. Or squeeze it. Maybe I managed to squeeze it. Then I should replace k plus 1 and k plus 2. Next, yeah? So these braids, really, you have to kind of first make one braid, then that's next braid. OK? And then I should replace k and k plus 1 again. And I managed, wow. OK. So if you don't know what I did, then now it's the time to say stop.
Is there some significance to the fact that on the right-hand side, the braid has the crossing the other way?
That's not good. Yeah. Very nice that you spotted that. That's actually pretty bad. That would be b minus 1. So one has to get the crossings correct. OK. Any other errors which you can spot? OK. So let's try to do the other one. And then let's see if you actually can see why they are the same, or if they are the same. I mean, they wouldn't have a name if they wouldn't be the same. So now we should replace first k and k plus 1. And I hope I do it correctly this time. Then replace, and then again this one. Okay. So these gaps have to be kind of clearly visible, and otherwise you never know if I do the counterclockwise or the clockwise exchange. Okay, can anybody see why they're the same? Otherwise I start using colors. I mean, in order to be the same, they should end up at the same final spot. Because otherwise, so this particle should end up here, and this particle should end up here. That's good. Okay. I just redraw it in some more smoothed out fashion. I'm allowed to actually deform it. Okay. I mean, I didn't tell you the geometric rules, but the geometric rules is that they actually make the same knot, but not so much important how they do it microscopically. So I just redraw this in a more straight fashion. Okay. Okay. Okay, yeah?
I think to see that the yellow line, which comes from the k plus 2, is below under all of the
Exactly.
strings.
So this is in the very back, yeah? The yellow is the very back. I hope all of you can see.
And then you can deform it as you like.
Yeah, and the red one is in the very front. And the orange line is in between. But the orange line, of course, I can move across, yeah? Actually, now in this break group, you can actually solve many of these puzzles which you might get in, I don't know, in some shops where there's some knots inside. Okay. And it's very often reduced to Young-Baxter equation, how you can actually get rid of the knot. Okay. So, understood? So, I convince you Young-Baxter is correct. This one is correct. The claim, which I don't convince you, is that given these two constraints on the free group, you have the break group. So trust me on that. So now we ask a very complicated question or important question. So first is the following. Exchange statistics is just a way how the braid group acts on the wave function. And this is what one calls representation, because you know the break group is kind of an abstract object. If I give you a wave function, you kind of have to tell me what each of these abstract objects does exactly on the wave function. And the thing which you tell me should actually also obey these rules. And that's what one calls representation. So, I mean, you know what a representation is. You know that very abstractly, I never know which direction, but very abstractly, x and p commute like this. Okay? That's abstract true. And you know that if you take wave functions, then you can say x, let's say this abstract object, we call it like this. You know, physicists never distinguish between the abstract object and the representations of the abstract objects. That's kind of the, or very often not. Okay. So the right-hand side is a representation of whatever is left. Okay. And the same thing you have to do here. You kind of have to define, if I give you a wave function, what do these objects correspond to? Okay? So now there's a dependence on space if you look at exchange statistics. Again, exchange statistics is how does your wave function deform if you swap two particles. And importantly, you have to keep the particles far away from each other while swapping. Otherwise, it's not universal what will happen. So in 1D, what do you think, what is kind of this swapping operation in 1D? You have one spatial dimension, you try to swap particle 1 with particle 2, keeping it very far away from each other. There's no, yeah. So there's no exchange statistic. Or it's a not well-defined concept, yeah. And you might have heard about bosonization in 1D. That's exactly because of that. You know, in 1D you can kind of change bosons into fermions and back to bosons. There's also Jordan-Wigner you make out of, I don't know, fermion spins. But, I mean, all the other stuff works in 1D. So the concept of bosons and fermions and so is not so well defined in 1D. So in 2D, and that were the plots all the time, you know? I mean, I kind of made a 3D plot for you on a 2D blackboard. It was a 3D plot where one dimension was time, and the other two dimensions were space. So there is obviously the break group. Or exchanging to particle acts on a wave function like a representation of the break group. But okay. So now we come back to 3D. You think in 3D it's kind of still the break group which is important, or there's some problem of the concept which, as I explained it to you up to now, which doesn't make sense in 3D? Yeah?
I would say it's still a break group, but it's breaking down to the symmetric group.
Yeah, okay, this is true. It's always the break group. But the concept which actually doesn't make sense, you know which concept doesn't make sense?
Yeah, I mean, in 3D you can always deform the knots to being the identity operation.
Okay, yeah, that if you know that, then okay, that's very hard for me to know because I would have to have a 4-dimensional blackboard to actually show it to you. The point is the following: the notion exchanging to particles counterclockwise and clockwise, this notion doesn't make sense in 3D, no? So, I mean, if I exchange two particles counterclockwise in a 2D surface, I can say there's one direction like this. And then I know what counterclockwise is. In 3D, it depends on the observer, if you might call it like this. And he might be completely turned in space, and nobody forbids that. And he shouldn't get a different outcome. That wouldn't be very good for a break group. So what turns out in 3D is that actually exchanging it clockwise is the same as exchanging it counterclockwise. Okay, so the inverse operation is exchanging it counterclockwise, which actually gives an additional constraint on the break group, that this is the identity. And the break group with this additional constraint reduces to the permutation group or symmetric group, how you call it. So then you get the symmetric group. And that's what is discussed in most of the textbooks. And it's correct in 3D or 4D. But there's something special about 2D. I mean, this you also have to trust me, but kind of, it's not very hard to figure out that actually these relations still hold in the permutation group. And the only difference in the permutation group is that kind of, there's no notion of kind of exchanging like this, and the inverse is kind of obviously the same, which is this. And then you get the permutation group. And once you have the permutation group, you only get bosons and fermions. So if you ask yourself about the representation of the permutation group, you only get bosons. Or some of you look a bit confused, yeah?
The bosons and fermions are also defined through the spin, right?
Yeah, but that I cannot get. Because in order that you can actually prove that theorem, which is called the spin statistic theorem, you need to know about field theory, and you have to know about field theories which are Lorentz invariant. So this theorem can only be proven in Lorentz invariant field theories.
But the definition still holds for the TD?
The spin statistic theorem.
That I can claim that bosons such integer spin and because the Majorana has zero spin, right?
Yeah, but we also don't have a relativistic field here. As soon as you break Lorentz invariance, the spin statistic theorem doesn't hold anymore. Okay. And in all solid-state devices, Lorentz invariance is broken by the lattice. Okay. So this spin statistic theorem is very important for high-energy physicists, and I don't know if it's at all important for condensed matter physicists. Again, because the lattice, which usually is behind your Hamiltonian, you never write down. It just breaks Lorentz invariance. So now we try to find representations of the break group. Yeah. So we go now in 2D. And we kind of try to figure out how could possibly the break group act on the wave function. That's what is called a representation. And in general, as far as I know, kind of classifying all representations of the break group is still an unsolved problem, so we will not be able to solve it here. But you see, the special thing about bosons or fermions was the following. The representations were one-dimensional in the sense of if you exchange the particles, nothing happened to the wave function except for something in front of the wave function. So you might start with the same thing, just looking at one-dimensional representation. And then you might say all these operators, bk, should just act like giving some kind of phase. Via phase, because typically things acting on wave functions should be kind of unitary, otherwise the normalization of the wave function goes away. So, understood? So you say, we imagine that now we have the additional freedom that we don't have this constraint, but we just have these two constraints. And we imagine what kind of phase factors we could give the wave function such that it actually is consistent with these two constraints. And in general, I could give every of this k a different phase factor. Might say, yeah, that's possible. Again, you see, if you demand that b is the same as its inverse, then this phase factor automatically becomes 0 pi, and you come back to bosons and fermions. But this is not what we demand. So then this part of the relation, that the commute, if j and k is larger than 2, you think this is fulfilled for this representation? Yeah? I mean, you see the bk is kind of multiplying with e to the ik, and then this is multiplying with e to the I theta j, or doing it the other way around. Do you think there's a difference? Complex numbers commute, no? Okay, because complex numbers commute, this is automatically fulfilled. So the only thing which you have to make sure is that actually Young-Baxter is fulfilled. And then we'll have all possible one-dimensional representations of the break group. So Young-Baxter tells me that e to the I theta k, e to the I theta k plus 1, e to the I theta k is equal to the e to the I theta k plus 1, e to the I theta k, e to the I. Okay. So what can I deduce from this relation? It's not so complicated as it looks. So I'm trying to figure out maybe something how theta k and theta k plus 1. I mean, I can simplify also both sides. Yeah. Exactly. Modulo 2 pi. So this phase is anyway only defined modulo 2 pi, but what I get out of it and because it holds for all k, Young-Baxter has to hold for all k, there's actually only one phase. Which would be surprising if it wouldn't be the case, because, I mean, it's exchange statistics, which relies on the fact that the particles are indistinguishable. So it would be very strange if kind of exchanging k and k plus 1 would give you a different phase as exchanging 1 and 2. Is this kind of how you derive this clear to everybody? I mean, you just solve it, and that's it. So all possible representation 1D is actually this, you see? I just have to take the k away from here. These are all possible one-dimensional representations. And one-dimensional representations are called abelian. And they're called abelian because the commutation is not of an issue. Yeah? So these are called abelian anyons. And anyons because they are not fermions and not bosons, but anyons. And they're bosons if theta equals 0, and they're fermions if theta equals pi. But in 2D, there's a possibility you can kind of get any other phase in between. And why can you get that? Because, again, the important thing why you could only get a plus or a minus 1, if you look back in your lecture notes, was the fact that actually exchanging clockwise and counterclockwise was the same, which was the fact that exchanging them twice should give you the identity, which in 2D doesn't necessarily hold. You kind of move them twice around, and this is still a braid. You kind of, it's kind of twisted arms. You cannot get rid of that. Okay. So these are all the one-dimensional representations, and they're called abelian anyons, and they're not of any interest for computation because you see how simple they are. I mean, they just multiply wave factors there, and there's nothing which you can imagine happens here by braiding them around, which you cannot calculate on a piece of paper in like 5 seconds or so. So there's definitely no computational power in this one. The question is now, what exchange statistics do these Majorana fermions have? Okay. And I try to convince you that, I mean, I show you a certain representation of the braid group which acts on the Majorana wave function. And you will check as an exercise that it really is a representation. And I try to convince you this is actually the correct one in this lecture, but I will not be able to kind of cover all points. If you're actually interested to learn a bit more about this, then I can point you to a reference on archive, which is 1111 and no 11 anymore, 6001. So the first question is, what do you do at all? If you have like particles defined like this, and you want to figure out what happens if you exchange them, like calculation-wise, yeah? Mm-hmm.
So we have shown that in order to satisfy this relation, we obtain this form of theta. But then we also say that if j and k are
This one?
Yeah.
No. I didn't say that they cannot commute if they're the neighboring ones.
Okay.
I mean,
Because I understand that the problem is that if they are the neighboring ones,
yeah, in the group they don't commute, but in the representation they can commute. I mean, it's not the case that that if they're not commuting the operators in the group doesn't necessarily mean they shouldn't commute in the representation. Yeah. Of course, it's not the most general one. That's why I'm kind of hinting at. Yeah. So. It's actually the same for the permutation group. I mean, you also look at one-dimensional representations, and they don't commute in the group. Okay. So the question is now really, what do you calculate if you want to exchange these two particles? And the fact is you kind of have to write down a Hamiltonian where in time you exchange the particles, and then you can actually calculate what happens to the particles if you exchange them. But in order to get a statistics out as we have here, you have to do it very slowly. Okay? Because then it will not depend on what exact path you actually exchange. And this comes back to a concept which is called Berry phase.
Sorry.
Yeah.
Is it correct to say that this framework of representation theory is only valid if you assume that you have a fixed number of particles and you never create or destroy, in a sense, the Majoranas?
Yeah, I mean, yes and no. I mean, the break group, of course, is here, yeah. So you kind of initially created them and destroyed them. And it's true. So kind of really actively you can only have a part of it. But once you destroy, you kind of get a finite, typically, a well-defined outcome here, and you can still treat the rest of the strands going up. Or just move whatever, whenever you kind of annihilated them to the same time. So the braid is kind of the same. You can move them up in time and kind of just make sure that you annihilate all of them at the same time. Yeah. So you can just deform all the braids in such a way there's one initial time where it generates all the particles and one final time where you annihilate all the particles. And the central assumption is that it kind of doesn't depend on how you deform this picture. Okay. I also lost count of the counting, but maybe Berry phase. And I might assume that most of you have heard about Berry phase. And in principle, it's not very difficult to derive what I'm going to present. But it will just take a bit too long. So you will find it in actually many textbooks. So there's an abelian version of the Berry phase and a non-abelian version. And I'm actually interested in the non-abelian version because it actually exactly corresponds to this energy diagram which we have. So if you kind of have certain low-lying states, I don't know. So let's call this energy and this time. And then you have a certain gap, and all the states are up here. And then you have some special states, I don't know, 2 of them. Whose dependence on time, and this is always adiabatic, so instantaneous energy. I mean, they might have some motion, but they're always staying degenerate. Or they don't have to have a motion. This is exactly this concept here. Yeah? So kind of the Majoranas, they never split if you do the braiding operation, keeping them very far away from each other. So we'll always have a doubly degenerate ground state. Okay? And then there's a gap, and the rest of the excitations are above the gap. So then the question is the following. You see, you start out in a certain state, for example, the brown or the red state. So you do this time evolution with a time-dependent Hamiltonian, which depends on some parameter. And you do it slowly. What means slowly? You do it such slowly that there's never a transition from here to here. So there's something called adiabatic theorem, which kind of tells you how slowly you should do it, and that you can really achieve this, that in the end you end up here again, in one of the two states. So if you wouldn't have this degeneracy of the ground state, then there would be only a phase which would matter. And that's Berry phase, because for a long time one actually thought that even this phase doesn't matter because it's a phase in front of a wave function, so why would you care? But in the case where you actually have the doubly degenerate state, there's not just a phase, because you could start with the brown state and end up in the red state, or you might end up in a superposition of the brown and the red state. So the question is the following, given the Schrödinger equation, you solve it in a time-dependent fashion. That's a complicated way to do. Or you say, okay, the change in the parameter is so slow that I stay in the ground state manifold. So I actually know in the end I will stay in one of the two instantaneous states back here. Then you might ask yourself the following. So if I start initially at time equals 0 at the instantaneous state alpha, maybe I should denote it the other way. If you start at time equals 0 at the instantaneous state alpha, and then you do the full time evolution to some large time here, such that the evolution is actually slow with this Hamiltonian. And of course, in order to do that, you have to have, of course, the time ordering. It's a time-dependent Schrödinger equation. The Hamiltonian depends on time, so you need to do time ordering and all this kind of stuff. So you end up with a state at time t. And now you know from the adiabatic theorem, this state at time t is actually some superposition of the states here, of the instantaneous states. And the superposition is actually always a bit confused, I think it's the beta typically here with some unitary operator. Why unitary? Because the wave function initially was normalized, and it will be also normalized in the end. So this is the superposition which you get out after this time t. And then there's some phase factor, which I write here. So this unitary only makes sense up to a phase factor. And there are many things which kind of come in this phase factor. And the phase factor is absolutely not topological at all. So the phase factor not just depends on the braid. But this unitary operator depends just on the braid. And that's actually, let me erase something. Something which I maybe just give you a hint why this is the case. Because what Berry, and in this more general context, actually Wilczek and C showed, that the U actually only depends on the trajectory of this parameter. So in general, you have many, many parameters, but not on how exactly your timing on the trajectories. So it's a completely geometric quantity. So the fact is that you can write the U so this just comes out of this Wilczek and C is a geometric quantity. And you know this type of geometric quantities from the Arnold-Bohm effect. It's a non-abelian version of the Arnold-Bohm effect. And that's why you have to have path ordering here, because these A's are actually not just numbers, but they are actually matrices. And so the vector index corresponds to this gradient operation. I think I'm missing an I here. And the two matrix indices correspond to the fact that our ground state manifold has actually more than one state. So in this case, two states. So it's actually a 2 by 2 matrix in our case. So you have to start integrating this, but then you have to path order. You integrate a little bit, and then you order the matrices properly. And then you get the complete evolution at the end. Important fact is this doesn't depend on, you see the time is dropped out. And the fact that it doesn't depend on the braid is a bit more tricky. And there you need a bit more differential geometry. So you also know from Arnold-Bohm effect, it actually, you can shrink and deform the contour unless you have a flux somewhere. So it's actually not the A field which determines, but in the end the B field and the E field. So the idea is that kind of you calculate the non-abelian corresponding field tensor from this, and the field tensor will be only non-zero very close to these particles. So as long as you deform the contours far away from the particles, this U will be always the same. So that's the general idea. So you see there are many steps involved in actually convincing you that this might hold. This is a theorem, so there's nothing to discuss about that. The question is whether this field tensor is really only non-zero close to the particles. And the other question is, how can we calculate this now for our specific setup? And then there's this statement that if you calculate this properly, whatever comes out will be actually a representation of the break group. Kind of in order consistency to work. Because in the end, you're kind of discussing topological properties of these braids in space-time. Okay, I know that this is a bit more tricky to swallow, but maybe you still have some questions regarding that. Yeah.
Just to divide this equation, did you use, is it general because you said, or did you use?
We used the adiabatic theorem. Okay. Yeah, I mean, I'm not claiming this is the general solution to time-dependent Schrödinger equation. Otherwise, I would get famous. No, what you do is really you plug this in here under the assumption that this is actually a superposition of that. And I can assure you, you just do a few lines of calculation and you can derive this yourself. It's actually not complicated at all. But you have to use the adiabatic theorem. And proving the adiabatic theorem, I don't know if you know, that's maybe a bit harder than proving this at the end. Okay. So the question is, what to calculate. Like, I started with these wires, which are now, I think, got rid of finally, which were in one dimension. And I then told you that in one dimension I cannot even braid the particles around each other. So I show you now what's the idea which people came up, that even in the setting of these Majorana wires, where you actually have the Hamiltonian, the Kitaev, how you can braid them, and then you can really go home and calculate this quantity, which maybe is a bit painful, or you look it up in this paper. And then you figure out what is the exchange operation doing on the Majorana Fermis, yes? 1,111.6001. Okay, and the idea how to braid these particles around each other is actually the same way as even though trains are on train tracks, you can actually exchange two trains on the train track. Yeah.
I have a question concerning this exchange. So what you assume now that you exchange the particles such that they really interchange their positions
Yes.
in the end. What happens if you do this not completely, or let's say you just exchange them halfway? And,
then it's not a well-defined braid operator. So the point is it's the same as in the Arnold-Bohm effect. So only the complete braid is gauge invariant. Yeah, you really have to start somewhere, do a braid, and annihilate them. All the other properties, whatever, depend on what exactly you do, what phases you give the wave functions. I mean, there are many things which you might do, but kind of the final outcome of a physical measurement, that doesn't change. I mean, if I ask yourself, what is if a particle goes halfway around the Arnold-Bohm loop? Okay, it depends on your gauge, yeah? So depending on how you implement the magnetic field in terms of gauge fields, you get a different answer. It's the same thing here. So you really, in order to do topological quantum computation, you really have to do this braid in space-time, like starting and braiding and annihilating at the end. Otherwise, it just depends on your concrete implementation. Yeah?
Okay, but then, I mean, in any experiment, I will never be able to exchange these particles precisely. So I will always...
You don't have to do it precisely, you see? It's a knot. In the end, it's a knot. I mean, maybe not this one. This one is not a knot. But in general, I mean, this is a bit too small. In general, if you do some braid operation, you actually see you have a knot in space-time, and there's no way you can get rid of that. You understand? No? Let me try to... I'm not very good in making knots, but I think maybe I need more of these in order to make a knot. Or is it enough? I think I need more of these. Or we can do later and take strings and try and make a knot out of them. You understand? So kind of the fact whether this does a computation or not really depends on the knot which you make in space-time. So there's something called Jones polynomial. Every knot corresponds to a knot, and the knot actually tells you what kind of unitary you do. And whether you made a knot or not, that doesn't depend on the microscopic details of your exchange operation. Okay? So in a sense, kind of, I just shown you that this even doesn't do a non-trivial operation, the braid which I've drawn here. But I should now come up with a more complicated braid. But you made knots, I guess, at some point in your life, and you figured out that there's no way to untangle them. This is actually the idea here. Instead of doing gates, you do knots in space-time. And every knot corresponds to a unitary operation. Okay. So let me, in the last 15 minutes, try to explain to you how to do this braiding with this Gitaev wire, because we just learned everything starting from that. There are other implementations of Majorana fermions. Then you have to do another calculation. And not all Majorana fermions are necessarily non-abelian particles, so it's actually good to do the calculation and check that they're non-abelian. And then afterwards, I will show you what is actually the representation. What is the form of the representation for the Majorana fermions? And in the exercise, you will check that it really forms a representation of the breakthrough. So I need one statement, which you also prove in the exercises. The statement is fusing 3 Majorana fermions. We saw fusing 2 Majorana fermions. So you gapped out. Both of them you could distinguish between the 0 and the 1 state. Fusing 3 Majorana fermions leaves 1 Majorana fermion behind. So if you bring 3 Majorana fermions very close together, closer than the coherence length, then 2 of the states gap out and 1 exact 0 state remains. Okay, it will be an exercise, and you will actually prove it. It's not too complicated. because what I need to get is the following. In order to exchange them, like the trains on a rail track, I need to have like a rail track like this and a rail track like this in order I can move one train like this and then move the other, then exchange. In order to manage that, I need to have a tree junction. Some people call it also T junction, but we like to call it Y junction. So then the idea is to have my runner here, my runner here, and then in the next step, moving the blue one down, and in the next step, yellow over and the blue up. I think that I can do in one step, and you understand yellow over and blue up. And I exchange them. I even know if I exchange them counterclockwise or clockwise. In this case, I exchange them counterclockwise. It really makes a difference. And you see where the difference comes from. It comes from this third part here. So the question is how to make this kind of junction here. And that's where I need to have this idea that fusing 3 Majorana fermions actually leaves a Majorana fermion behind. Okay, trust me on that. It will be very easy to prove, and there should be something left over for you to do. So. So the idea which one starts is the following idea. So one has one Kitaev wire. So this is the Kitaev wire with potentially 2 Majoranas at the end. And then one has another Kitaev wire with 2 Majoranas at the end. And another Kitaev wire with 2 Majoranas at the end. And this looks very similar to this Y junction. So I draw now, maybe with red, when I fuse 2 Majoranas. Okay? Fusing meaning bringing them together or coupling them strongly. So I actually fuse these 3 Majoranas. Fusing the 3 Majoranas leaves me with 1 Majoranas at the end. Okay? So now I have a junction where I have like 1, 2, 3, 4, no problem. Okay? We always need to have an even Majoranas. But kind of this Majorana is coupled with a Kitaev wire to this, and this Majorana. Okay? And now I can do this operation. So how can I manage that initially have the blue and the yellow Majorana? So what do I have to do to these 4 Majoranas which I have in order that I have a blue and a yellow only left and not 4? Somebody has an idea? I mean, you understand. So I want just to have 2 Majoranas. Now I have 1, 2, 3, and 4. That's a bit too much. Yeah?
Just turn off the bottom wire.
Yeah, so fuse these 2. I mean, in our language, how we learned, I mean, make this an insulator, or in other language, fuse the 2 Majorana fermions. Yeah? So if I fuse these 2 Majorana fermions, I fuse them, and I'm left with the yellow and the blue. Okay. So now could somebody explain to me how I can do the step from 1 to 2? What would you do, like operationally? What we have to do is to move the blue one down here. So what would you do? Any takers? I mean, what you can do, the rule of the game, you can make every white line to be a red line, okay? Just that we agree on the rules of the game. So I now made one Majoranas here out of the middle. So there's potentially a Majorana everywhere here. And I can make the white line red. And if I make it red, I fuse the two at the end. So what would you do to move the blue down here? Yeah.
So maybe you could kind of remove the P weight from the left.
So make this red or white?
So make it red.
Make this red?
So that the blue one goes to the middle and then make the lower one
This white. That's the right idea. So the wrong idea, just that you know the wrong idea, is make this one white and then this one red. Because if I make this, I mean, we start off with two Majorana fermions. So our ground state degeneracy is, okay, without superselection, forget about the superselection, is 2. So if you turn this white, then you change your ground state degeneracy. You're suddenly in more states than you had before. Very bad. Okay? So the correct first step is making this red. And then you said, yeah, it moves the blue to the middle. Is it really the case? What happens if I fuse 3 Majorana fermions? I mean, now I fuse 3 Majorana fermions, no? It leaves 1 Majorana fermion behind, but it's kind of a delocalized Majorana fermion. It kind of lives everywhere here. Okay? But again, all that I need is fusing 3 Majorana fermions, leaves 1 Majorana fermion behind. And then I turn this one white. Okay? And now I can be sure that it's actually blue one which arrived down here. Yeah? Yep. Yes?
Where's this third Majorana?
Which third?
I mean, the one that is delocalized. You start with...
This one? You see, at the process where I turn this one off, this one moves.
Yeah, but I mean, where's the third Majorana? I only see like the blue and yellow. Why there is a third Majorana?
There's never a third one. You see, there's a blue and a yellow here. The red one cancels these two. There's a blue and a yellow here. And there's a blue and a yellow here.
Okay, so it does not have anything to do to the 3 Majoranas.
At this initially, you mean?
Or because you said when going from these 3 pictures, you said like there is 3 Majoranas and then one needs to be...
Here, there are 3. Originally, there were 3, yeah? 1, 2, 3. But I fused them. So fusing 3 Majorana fermions is the same as having 1 Majorana fermion. So this is the first exchange operation. And then I guess you're, just next step is the same, next step is the same, and you move them around each other. So the Hamiltonian which described this is like you have an H0 here, and gamma 0, gamma 1, gamma 2, gamma 3. So the Hamiltonian is nothing than -1, gamma 0, and then some delta times the gamma. So fusing these two is delta 1, and these two is delta 2, and these two is delta 3. And if I draw the line red, then the delta is actually some delta bar. And if I draw it white, the delta is actually 0. And then you just take this Hamiltonian, make it time dependent, changing delta 1, delta 2, delta 3 in a time dependent fashion in order to do this correctly. And correctly means not turning the red off first and then the red on, but turning first this red on, then this red off, and so on and so forth. So then you get a Hamiltonian which depends on time in a 3-dimensional parameter space with delta 1, delta 2, delta 3. And you calculate this. Okay. Of course, there's some calculation to be needed. But if you know how to do it, actually, it's not even so tricky. But of course, if you do it the first time, It might take you a day. And at the end of the day, what comes out of that is actually the answer to this question here, at least for this setup. Okay, so there are people really thinking about doing these wires in Y junction. I think the people in Delft have already wires which look like this. So what comes out is what statistics do Majorana fermions have? And it turns out that this operation of exchanging the two Majorana fermions gives you a unitary operation which we call B of k if you exchange them counterclockwise. Again, we don't distinguish between the abstract group element and the representation because it's conventionally done like that in physics. So okay, that comes out after a long calculation. Okay, so for you to check in the exercise is, does this representation fulfill this relation, which doesn't have a name, and the Young-Baxter equation? So does it form a representation of the breakroom? And it's actually, in a sense, the Ising representations, or these are called Ising anyons. And they are non-abelian. And I think there are different ways to see that they're non-abelian, but one way is kind of looking at the square of this. So doing it twice. And I think we last time had a discussion that if this is enough or not, but and it's actually it's still something which is not proportional to the unit matrix. So it's not proportional to the unit matrix. And as far as I know, this is enough to show that it's actually non-abelian. Non-abelian means that there's no way that you kind of factorize, what's the idea of representation? We found the representation here. But then you say, yeah, I might find a subspace where this is actually reducible, how you call it. So you find a new basis such that that this doesn't act like something complicated like this, but more like these one-dimensional representations. So the idea is that you actually cannot factorize it and just describe it in terms of this one-dimensional representation which you've written down there. But you always have to have something which is not commuting. So then one of the questions is what kind of operations you can do with this. And there are all operations, all unitaries which you get by kind of multiplying these together. And sadly, they don't form like a dense subset of all unitaries which you might potentially do. And that comes together with the fact, which I actually told in the introduction, that here you need additionally like parity check measurements and this gate, but with an 8 instead of 4. And once you have these two additional gates, then you can kind of find any unitary. So you can find approximations like as close as you want to any unitary with just waiting around.
So from the point of view of representation theory, would you say, so the dimensionality of this non-abelian representation is this 2 to the power n over 2 that you introduced last time?
Yeah.
And you mentioned there are arguments that that's an irreducible representation.
Yeah, there are arguments that this is actually irreducible representation. And there's also something which is called quantum dimension, which is also related to that. It's like if you add a particle to it, how much more does the dimension grow? And you kind of write it as square root of 2 times the number of Majoranas. So that's kind of dimension of a Hilbert space. And there are some arguments which, as far as I understand, are not yet really completely proven, is the fact that this is just a square root of something, then they're always not universal for quantum computation. So Fibonacci has here more complicated behavior. But so the field is big, and there are many review articles, and depending on what part of the field you want to know a bit more, you can come afterwards to me, and maybe I can point you to a review article. So the idea of this lecture was just to give you like a general introduction to the field. Try to convince you that there are certain particles doing something like this in space-time. Actually, that's a unitary, and the unitary just depends on the kind of knot you make in this space-time trajectories and whether you can kind of disentangle it or not, and that you can actually do quantum computation with this. Okay, are there any questions left? We actually reached the time limit, so yeah.
Maybe the more implementation questions. If you have your nanowire, for example,
yeah.
I mean, usually it sits on a substrate, obviously insulating. So once you get minor fermions everywhere in the wire, I mean, when does the
So we learned that actually the Majorana fermions is this interface effect.
Yeah, but you usually have an interface along the whole wire, or will you have extend it in vacuum?
I mean, you're thinking already something else, that you have a superconductor on top. These are never talked about, yeah? You have a superconductor, and on top is a nanowire. And the short answer is, if you think about single particle excitations, as Majoranas are, yeah, then the superconductor is essentially like an insulator. There's no way a single particle can go in the superconductor. So it's essentially like putting an insulator close by, and then you wouldn't worry like you worry now. So that's the short answer. And you understand why it's an insulator, because the superconductor actually can only take electrons in pairs. Yeah. Are there any other urgent questions? Otherwise, I want to thank for your attention, and I hope you enjoyed the lecture.